Hi, everyone. We're about to start. Give it about 30 seconds while everybody's jumping into the webinar. And I'm going to hand this off to Arvind. Thanks for coming.
Thanks, Maury. Let's just give it 30 seconds for people to join in, and then we'll get started. All right, great. Let's get started. Welcome to this webinar. Thank you all for coming and for your interest in the feast modeling framework and the paths to equivalence effort. This is a public webinar. This is being recorded, and the video will be available for viewing a week after this webinar. I want to get started by introducing the people in this webinar today. My name is Arvind Ravikumar. I am an assistant professor of energy engineering at Harrisburg University, and I run the Sustainable Energy Development Lab, where we work on addressing methane emissions from the oil and gas sector through fieldwork, modeling, and policy analysis. This webinar is the culmination of a year-long effort known as Paths to Equivalence, in collaboration with scientists at Colorado State University. As part of this Path to Equivalence effort, we will be introducing the FEAST modeling framework, the latest version of the FEAST framework, as part of this webinar for use by the industry, regulators, and other scientists. Today from Harrisburg University, we have Chandler Kemp and Alan Strayer. Chandler Kemp is a senior scientist in the lab, and Alan Strayer is a graduate student. They'll both be leading the webinar and the tutorial portions of the session. From Colorado State University, we have Clay Bell, Jerry Dugan, Christine Bennett, and Daniel Zimmerly, who will discuss the future projects and what we are going ahead with this modeling framework and the path to equivalence effort. You have our emails on the title slide. So if you have any questions, please feel free to reach out to us. All right, so I'm going to give a very brief 1-minute introduction to what this webinar is about and some logistics, and then hand it over to Chandler Kemp and Alan Strayer to start with the webinar. So what is FEAST? For those of you who might not be aware, FEAST is the Fugitive Emissions Abatement Simulation tool. This tool was developed first at Stanford University about 4 years ago. Chandler and I were on the team that developed the first version, and this is the version 3.1 of that model with additional details into real-world performance. So what can the FEAST model do? The FEAST model was developed to evaluate new methane emissions detection technologies. It can design and compare methane policies such as leak detection and repair programs, and it can also assess the cost effectiveness of alternative emissions reductions approaches. And how the FEAST model does that is something you'll see in the next hour or so. How can all of you participate? There are different ways to participate. Some of you have already started working with FEAST, so you know exactly what's in this. Some of you might be new to this, and some of you might be curious on what this model can do for your future plans and your efforts. The first thing is use. The model is publicly available. The code and the documentation and the papers are available freely. They're regularly updated, and we are always here to provide you with any technical support you might need in using the model. So the best thing you can do for us is use the model and provide feedback. The second thing, equally important, collaborate. FEAST model, as you will soon see, uses a lot of data on methane emissions, on technology testing and technology parameters, and regulatory equivalence, looking at methane policies and understanding how to achieve equivalence. All of this require collaboration with the industry, with regulatory agencies and other scientists, and we welcome all of those things. Please reach out to us to work together on some of these issues. The last thing is fund. There's always new developments in the methane space. We want to put in new model features. We want to add in new technologies. We want to develop new evaluation tools so that this model is as useful, as broadly useful as possible to a wide audience. So that's it for an introduction to FEAST from my end. A couple of logistical issues for this webinar. Roughly, the webinar will be conducted in 2 parts. The first part is a general introduction to feast, capabilities, some modeled results and insights. This is for people who are new to feast and wants to learn what it can do and how it can be useful to them. We'll have a short Q&A at the end. That's the first part. It'll be the first hour of this webinar. The second hour is going to be a tutorial where we'll go into the details of loading feast, running feast, and looking at the results for practitioners. It's going to be a tutorial form where we'll walk you through the model and through running the model online and the resources that are available. All of you are welcome to stay, but some of you who might not be practitioners are free to leave after the first introductory hour of the webinar. Second thing, feel free to use the Q&A box to ask questions throughout the presentation. If you have a specific question, please indicate who they are for. There'll be 4 or 5 of us speaking throughout the 1-hour webinar. As I said before, this webinar is recorded and uploaded online and will be available for viewing next week. Most importantly, all feast-related materials, including links to model code, the slides that I'm using here, as well as papers based on feast, is available at this website. It's available right now, so if you go there, you can download it in case you're having problems accessing the live version of this webinar. With that, I'm going to stop. Welcome you all again to this webinar on feast release, and I'm going to hand it over to Chandler Kemp to start the webinar.
Great, thanks, Arvind. All right, so as Arvind said, I've been working with this model for several years now, and I'll spend the next 20 to 30 minutes giving an overview of what feast is, what's new, and what we can use it for, and what's new in this version of feast. Then I'll pass it on to Alan and Dan and Clay to discuss some other details of feast. So I'll give you a brief introduction of feast, and I'll restate that here. So feast is the Fugitive Emissions Abatement Simulation Toolkit. The toolkit provides a method for estimating methane emissions from oil and gas infrastructure under different leak detection and repair programs. The model uses gas field detection method and leak detection and repair program data to simulate emission scenarios. So first, if we think about infrastructure properties, in order to run the model, we need to specify things like the number of production sites we want to simulate, the type of equipment that's present at those sites, and the emission characteristics of that equipment. In addition to the infrastructure, we need to describe the detection methods. So detection methods are characterized by properties like the probability of detection curves, that is, how likely they are to detect emissions of different sizes, and perhaps their costs or how quickly they can identify emissions. Finally, we need to specify program attributes. So these attributes specify how the detection methods are deployed in the field. So for example, we might think about survey frequency as a property that must be specified in the simulation to characterize not just the detection method itself, but how it's used in practice. Feast then combines these 3 types of data to create a dynamic simulation of emissions through time. So an example of what a single iteration might look like is on the right. We have time on the x-axis, emissions on the y-axis, and then a scenario without a leak detection and repair program represented by the blue line, and then an OGI or optical gas imaging camera-based program represented by the orange line. And so in this example, we can see that in general, the emissions are reduced by the leak detection and repair program. And we can, if we integrate the difference between the emissions without leak detection and repair and emissions under the OGI program, we can quantify how much we expect this LDAR program to reduce emissions. So we can use the model to compare the mitigation potential of leak detection and repair programs. So here I'm showing results, example results from a paper that we released as a preprint just a few days ago. So in this example, in the plot, I'm showing survey frequency across the x-axis, fugitive emission mitigation percentage on the y-axis, and then 2 different leak detection and repair programs. The orange curve represents optical gas imaging surveys, and the purple curve represents an aerial plane-based survey with OGI follow-up. So in this example, I've shown a couple of key settings on the right. The median detection threshold for OGI we've chosen as 2 kilograms per day. So that means that an emission rate of 2 kilograms per day has a 50% probability of being detected, in comparison to the plane-based survey, which has a median detection threshold of 94 kilograms per day. So the plane is less sensitive than the OGI camera. However, the plane is also much faster. So the OGI camera in this example surveys 6 sites per day compared to the plane, which can survey over 200 sites per day. So now if we look back at the plot, we can see that for any given survey frequency, the plane results in less mitigation than the OGI camera. However, if we consider the dashed black lines at 40% and 60% mitigation, we can see that if the plane is dispatched more frequently than the OGI camera, you can achieve equivalent emissions mitigation. So by equivalent emissions mitigation, I mean that we're using a different LDAR program, in this case, a plane-based survey rather than an OGI survey, but we're still achieving the same, we're still mitigating the same amount of methane emissions. Feast also includes a model of program costs. And so as long as we have accurate cost data for an LDAR program, we can estimate the dollars per ton of CO2 equivalent emissions mitigation that a leak detection and repair program will incur. So for this example, we're assuming that an OGI survey has a cost of $600 per site compared to a plane-based survey that has a cost of $100 per site, in addition to the cost of any OGI follow-up surveys that are required. And specifically when I say OGI follow-up, I'm imagining a leak detection and repair program in which we have a plane that flies over natural gas infrastructure and identifies sites that have anomalously high emissions. But in order to actually identify the specific component that's leaking at that site, in this example scenario, we're saying that an OGI camera team must be dispatched to the site to identify the specific problematic components. So now if we shift and look at the plot, we have survey frequency again on the x-axis, same as before, but now mitigation cost on the y-axis. And we can see the 2 example dashed lines from the previous slide. So for a 60% mitigation with a plane-based survey, we're expecting to need about 9 surveys per year to achieve that level of mitigation, which results in a mitigation cost of around $23 per ton of CO2 equivalent. We can compare that to an OGI survey, which achieves the same level, 60% level of mitigation with 2 surveys per year at a somewhat lower mitigation cost. In contrast, if we look at a scenario in which 40% of the emissions are mitigated, that only requires 3 surveys per year, and the plane-based survey is actually somewhat less expensive than the equivalent OGI leak detection and repair program. Again, that's given the assumptions that are detailed in this example. So we can imagine in real world leak detection and repair programs, the costs might be different and the sensitivities might be somewhat different, resulting in different answers. But the takeaway from this slide is that given accurate cost data and given accurate detection threshold data, we can estimate the conditions that are required in order to achieve equivalent mitigation with a new leak detection and repair program. So at this point, I want to pause, and I set up a couple of poll questions that I think Mari can bring up. And this is to get a sense of who's on this call. I want to see what sort of experience you have with Feast and what part of the natural gas industry you work in.
Chandler, could you quickly mention what type of sites were simulated for this particular set of slides?
Yeah, great. Thanks, Dan. So for this set of slides, we're looking at production sites. So they have production wells, tanks, other equipment typically associated with production sites. And in this example, we're drawing the number of wells per site from a distribution that ranges from 1 to 50 wells per site. So I'll give you a few more minutes to record your answers here. It looks like we've got about 2/3 of people have voted so far. Mario, if I end the polling, will the attendees be able to see the results?
Yes, I'd be happy to. I'll, as soon as I end the polling, we'll do that.
Okay, great. Just give it 5 more seconds here.
Okay. I'll share results.
Great. So I think you should be able to see the results now. And so we've got a nice collection of people here. We have about a quarter detection method developers, about a quarter in the oil and gas production companies, a few people in oil and gas field services, and a quarter regulators. And a broad range of experience with Feast here as well. So about a third of you just learned what Feast is 2 slides ago. If you have heard about it before, and 10% have run simulations using Feast before. So that's great. And if you're interested in getting more involved with Feast, like Arvind said, you can always reach out to us, and we're eager to help people get more familiar with the model. And Mari, can you confirm that people are still able to see my screen?
Yes, yes, you can.
Great. All right. So moving on, the next section of Feast, next section of the presentation, I'm going to describe what type of data Feast relies on. So Feast requires the user to provide emission characteristics, infrastructure activity counts, and leak detection and repair program specifications. We do include example data sets in Feast, but they should be customized to unique applications. So the data sets that are included in the model are really meant to give users a sense of how the data can be structured if they're going to be used in Feast. We would encourage developing unique data sets for specific locations or questions. So infrastructure is characterized by the number of components at each site. So what I mean by that is Feast considers 2 levels of infrastructure. The first level are components. These are the specific parts of a facility that may emit methane. Examples include things like valves, thief hatches, flares, etc. Sites are represented by a collection of components in close physical proximity to each other. And the site level of infrastructure is relevant because some detection methods will be sensitive to emissions at that scale. So you might think of a truck or an aerial-based system that detects total emissions from a site rather than from an individual component. So a simulation may include many types of components with different emissions distributions. So for example, we might think about fugitive or components that are likely to emit fugitive emissions as having one set of emission characteristics, and then flares or perhaps a wellhead that unloads. These would have very different emission characteristics, and they can be represented in Feast by specifying different parameters for those components. And finally, once all the types of components are defined for a particular set of infrastructure, they can be grouped to make unique sites and then used in a simulation. So I alluded to this just now, but emissions can include both vents and leaks. Vents refer to emissions that will not be repaired even if they are detected, whereas leaks will be repaired if they are detected. And these are represented at the component level in Feast. So even if we're considering a technology that looks at site level emissions, in Feast, those site level emissions arise as a sum of component level emissions in the simulation. Emissions are characterized by the rate at which they occur, the distribution of sizes of the emissions that we would expect from a particular component, and the duration of those emissions. Once these parameters are defined, Feast uses a stochastic emissions model. And so by stochastic, I mean that we're defining for example, the rate at which new leaks occur, and then randomly choosing the exact times when an emission starts based on that rate. This is in contrast to a process-based model that would consider the physics or the underlying process that leads to emissions. But that being said, feast is designed, we're working closely with Colorado State University and the University of Texas to make sure that feast can be coupled with a process-based model if we want to explore the effect of vented emissions more accurately. So to give you a visualization of the type of data that's going into feast, I'm showing a plot here that's the cumulative emission rate distribution that's been observed across 5 peer-reviewed emission surveys. So on the x-axis, I have the emission rate in kilograms per day. On the y-axis, I have the cumulative percent of emissions that are less than or equal to the relevant value on the x-axis. The dark curve represents the component emissions distribution. And one of the key takeaways that's been well documented over the last several years is that emission distributions tend to be heavily skewed. That is, the top 5% of emitters can account for 50% or so of the total emissions from natural gas infrastructure. And so it's critical to use this emission rate distribution rather than a single emission factor, because the heavily skewed nature of the distribution has large impacts on the performance of different technologies. The gray curve that I'm showing is the emergent site level emission distribution that arises in feast simulations, or specifically in this example simulation. And you'll see that it's shifted to the right because a site may have more than one component emission, resulting in generally larger, the total emissions from a site are greater than the emissions from individual components. So the next class of input data to feast are technology sensitivity and dispatch rules. So there's we simulate several different types of technologies in feast. The first are survey-based methods. So that's any method that is dispatched periodically to look at a set of infrastructure. The second class are continuous monitor methods. So these are methods that are set up on site and continuously search for emissions. In addition, we can distinguish between site level detection methods and component level detection methods. So a site level method is sensitive to total emissions from a site, whereas a component level method is sensitive to emissions from an individual component. And these different types of leak detection and repair programs require different inputs. For all survey-based methods, we require a probability of detection curve or surface. So this is going to define the probability that an emission will be detected by a particular method depending on the size of the emission. And we also allow users to specify a probability of detection that depends on meteorological conditions as well as the emission rate. And survey-based methods must also have a survey interval defined. That is, how often is this method going to be dispatched to look for leaks? In contrast, a continuous monitor method requires a time to detection curve or surface rather than a probability of detection curve. It works similarly in practice, but the idea here is that the user needs to specify for a given size of emission what the average time will be before a continuous monitor can detect that emission. So that's the distinction between a survey-based method and a continuous monitor-based method. The survey-based method needs a probability of detection curve, whereas a continuous monitor needs a time to detection curve. There's also a distinction between component and site level methods. For a site level method in feast, we require a component level follow-up method that's associated with the site level method to pinpoint leaks. And that allows the model to know exactly which leaks should be repaired based on detections. Finally, all methods may have an operating envelope that's based on meteorological conditions. So an operating envelope tells feast what conditions the detection method can be deployed under. So a great example is that many technologies are less effective at high wind speeds. And so you might define an operating envelope and that only allows the method to be dispatched if the wind speed is below, say, 20 meters per second. So here I wanted to give you an example of how we can go from real empirical data to a probability of detection curve. So I've pulled this figure from a paper that Dan Zimmerli released just last year. And it shows the probability that an OGI camera will detect emissions of different sizes. So on the x-axis, I have emission rate, and on the y-axis, I have the observed detection fraction. That is the fraction of emissions of that size that were detected in empirical trials of OGI cameras at METEC. So this dashed purple line gives the best fit to the data, and that's what would need to be input into Feast. So a user could pull out a set of points along the dashed purple line and pass them to Feast, giving the emission rate and the probability of detection. And Feast would then use those data points to interpolate between them, determine the probability that any particular emission in the simulation is detected by an OGI survey. You could take this a step further if you had the data to support it by giving a probability that was specific not just to the emission rate, but also to a meteorological condition such as wind speed. So I wanted to touch briefly here on what the key sources of uncertainty are in the model. Of course, number one, I want to point out that the quality of input data is paramount. So the results that we get out of Feast are only as good as the data that goes into it. And so the more we're able to collaborate with operators and technology developers to make sure that we can use accurate data in our simulations, the more confident we can be in results. And so this input data really helps to reduce the uncertainty surrounding, excuse me, surrounding metaparameters in Feast. So by metaparameters, I mean things like the leak production rate for a specific type of component, or the emission distribution for a specific component, and also properties of detection methods. So the probability of detection curve is a metaparameter. And improving the quality of input data helps us minimize uncertainty around these parameters so these are parameters that are set at the beginning of a simulation and don't change. There's a second type of uncertainty in Feast that is due to inherently stochastic processes. And so a fugitive emission is a great example of that, where it's inherently random when a particular fugitive emission will start. And so Feast models that type of uncertainty by using probabilistic simulations. And you can explore the range of uncertainty by running many Monte Carlo iterations with the same metaparameters. So the takeaway here is that we've got two different types of uncertainty in Feast. And one are these metaparameters, the simulation settings for the model, and the second are inherently stochastic processes in the model. But most importantly, the better input data we have, the better we're able to specify these metaparameters, and the more confident we can be in the results. So that concludes my summary of how the Feast model works and the types of data that go into it. And I'm going to spend a few minutes now highlighting the new features of version 3.1. This is the public release of this version of Feast. It's available for download through GitHub at the link here. And again, these links are all available through the slides that are posted on Arvin's website. You can look at a preprint with detailed simulations using Feast at this link. And finally, you can get an overview of the model through Arvin's website that's listed here. So this table, I'm not going to go through this table in detail, but it will be available online if you want to review it or refer to it later. But the point is that Feast has gone through 4 different releases, starting in 2016 up until version 3.1 that we're releasing now. And there's a few critical new features in this latest version of Feast. And those are highlighted on this slide. So the first key revision is that we now support modular leak detection and repair programs composed of detection methods, repair methods, and dispatch rules. So what that means is you can define as many different detection methods as you want and combine them all into one leak detection and repair program. So you might have an OGI camera survey coupled with a plane survey, coupled with a continuous monitor at a few key sites. And those would all be included in a single leak detection and repair program. we're also supporting an operating envelope for the first time in this version of Feast. And so that I mentioned that before, but it gives you the ability to set meteorological conditions under which a particular detection method cannot be deployed. We're also supporting probability of detection surfaces with 2 independent axes. So this is, again, referring to a probability of detection function that can depend on not only the emission rate, but also a meteorological condition like wind speed. We are also now supporting detection and repair methods with queues and finite survey time for sites and components. So the queues are important because it allows, say, a plane-based site level survey to pass a set of sites to a queue for a follow-up team, a follow-up ground crew to look at. And so this is part of supporting modular leak detection and repair programs with methods that can communicate with each other. So in order to support the operating envelopes and probability detection function with 2 independent axes, we need to pull meteorological data into Feast. And so we're supporting this by allowing users to provide a typical meteorological year data set to the model, which then simulates all meteorological conditions throughout the simulation. So typical meteorological year data sets are available from the National Renewable Energy Lab for many locations throughout the United States. And finally, this release is supporting continuous monitoring methods with empirical time to detection data. So these are 6 critical new features that we're releasing in this version 3.1. So finally, I want to look at a quick example here that highlights what results can look like from Feast and what the new version of Feast supports. So for this example, we'll consider 100 production sites with 1 to 50 wells per site. We'll simulate a plane-based survey method with OGI follow-up, a continuous monitor method with OGI follow-up, and a more conventional OGI survey method. And these 3 different types of detection methods will have a large range of detection thresholds. So finally, this is what results can look like. So in Feast, so on the x-axis, I'm looking at different leak detection and repair programs. On the y-axis, I have fugitive mitigation percentage. And across the top, I've labeled 3 different versions of Feast. So in the first version, 2.0, we didn't support tiered programs. And so out of the 3 LDAR programs that we're considering here, only the OGI survey method could be simulated. In Feast 3.0, we did support, so Feast 3.0 was released about a year ago, and it supported tiered detection methods. So you could have a site level method that would trigger ground crew follow-up actions. And that is, so those 2 methods could be simulated in Feast 3.0. And finally, in Feast 3.1, we're also now supporting continuous monitor methods. You can see this range in results for each LDAR program, and that's due to the stochastic simulations in Feast. So I've run many iterations of the model, and we get a range of results back. So I want the takeaway from this slide to be sort of the progression and what we've supported from Feast, and the type of results that we can expect to see. The actual comparison between detection methods is not particularly meaningful in this example because I haven't described what the full set of assumptions are. So with that, I've got one more poll question that Mari can bring up here. And it's, can we get the, I think there's a 3rd question that's not part of this set.
Sorry about that. I'm trying to do that. I'm not sure why it's not coming up with the 2nd one. Bear with me and I'll try to fix it. Otherwise, can you keep going?
Yep, no problem. So this question is about what types of LDAR programs are oh, here we go. So the question is, which of the following leak detection and repair programs is not supported in Feast 3.1? So this is a bit of a pop quiz, but also hopefully motivation for the next section of the presentation, where Alan Strayer will present future steps, or next steps. So as you're thinking about this question, think back to the type. So remember that Feast supports a few classes of leak detection and repair programs. These include site level surveys, component level surveys, and continuous monitor methods. And I'll just give you 5 more seconds to give an answer. You've got about 2/3 of you have responded so far.
Not everybody likes tests, huh?
Yeah, that's okay.
Shall I end the polling?
Yeah, go ahead and end it. Thanks. All right, so let's talk through this a bit. We've got a few respondents for every option. So for case A, a continuous monitor method that dispatches an OGI team to sites with high emissions. That is supported by Feast. So in the continuous monitor module that we are releasing in this version, the continuous monitor monitors sites for the total emissions from that site, and then we'll dispatch an OGI team if if there's a detection at that site. So A is covered. B could be a bit tricky because I said a drone that identifies leaking components from the air. As far as Feast is concerned, it doesn't really make much difference whether it's from the air or anywhere else. But Feast will model this as a component level survey-based method. And so as long as we can define a probability detection curve for that drone, then Feast can simulate it in a meaningful way. Option C, an aerial survey that quantifies emissions from the air and compares observations to expected site level emissions, is not supported in this version. So that's because we're not supporting quantification in Feast 3.1. And Alan's going to speak to that in a moment because we are hoping to include that in the next version of Feast. And then finally, annual OGI surveys coupled with more frequent aerial surveys. That is supported in Feast 3.1, and that's a new capability of this release of Feast to couple multiple types of detection methods in one leak detection and repair program. So thanks for answering those questions. And C was the correct answer. We're not supporting quantification in Feast 3.1. And with that, I will pass this on to Alan Strayer to talk about future work in Feast. He'll be leading development for Feast 3.2. I'll go ahead and let you share your screen, Alan.
All right, thank you, Chandler. Bear with me one moment while I bring this up. All right, are my slides up now?
Yes, they are.
Excellent. All right, so as Chandler alluded to, I'm Alan Strayer, and I'll be leading up the future development of Feast 3.2. Chandler's provided you with an excellent look into what Feast currently is and its capabilities. I'm just going to take a brief moment to talk a little bit about what we have in the pipeline for the future of Feast. So as Chandler alluded to, we're looking to implement quantification-based dispatch decisions in Feast 3.2. we'll be looking further down the line into multi-gas species simulation, support for satellite-based detection technologies, and I'll touch a little bit on co-simulation with methane emission with the methane emission estimation tool, also known as MEET. So getting into what quantification-based dispatch decisions are, what, why, and why we'd be implementing that. This feature is motivated by findings that leaks represent only a small portion of emissions from some sites. So say you have an aerial survey going on, a plane flies overhead and it detects an emission. The way that Feast currently works is it's going to tag that emission and say, okay, we've detected this emission, so now we're going to release a ground OGI survey team to evaluate what is leaking and whether or not that can be fixed. However, if you know the baseline emissions for a particular site, and the emissions don't exceed that, if it's not an anomalous emission, then you don't need to dispatch. And so with this feature, we're implementing the capability of site level surveys to be able to make that decision based on the emission that's detected at the site level. Moving on to multi-gas species simulations, Feast can currently only simulate fluxes of methane gas. However, we are aware that multiple gas species are present at the wellhead and that tracking them may be of interest. So it makes sense that if there are detection technologies that are sensitive to these gases, we should be able to provide the ability to simulate them in Feast as well, as there may be interest in mitigating the release of those gases to the atmosphere as well, not just methane. And getting into support for satellite-based detection technology. Satellite technology is really coming online now. It's becoming a much bigger thing, I guess we could say. And as that's happening, this increase in activity, we expect to be able to obtain sufficient data to be able to calibrate satellite simulations within Feast. This will also come with the integration of support for GIS data into the model, as this will be necessary for modeling satellite detection methods. It will also allow for more complex tiered detection simulations, such as you could have a satellite trigger a plane survey that could trigger an OGI follow-up and be able to model the cost and effectiveness of such an LDAR strategy. And finally, looking into MEET Feast co-simulation, this project serves as an example of how a process-based emissions model can be integrated into the Feast framework. In this case, we're integrating the methane emissions estimation toolkit, or MEET. It's being developed at the University of Texas and Colorado State University. So here, the MEET model generates emissions from a prototypical facility, and those emissions are then fed into the Feast model to evaluate the efficacy of LDAR programs in mitigating emissions from those sites. So that was kind of a quick, brief overview of what's ahead for Feast. So if you have any questions, please feel free to ask them in the Q&A, and I'll hand over the presentation to Dan.
Thanks, and we'll see if we can make, you're going to unshare, right? And then I'm going to share mine.
Yes, let me stop share. All right.
Okay, here we go. Okay, is that up on the screen?
Yes, it is, Dan.
Great. So we're going to pop up a little bit higher level now, just for a moment. And I'm going to talk a little bit about the broader program. And because we've sort of started with Feast in the middle of the pathway to equivalence, and I'm going to just kind of go out in both directions and sort of put things into context beyond just the Feast development we're talking about right here. So the first thing is, as you all know, and just looking through the names of the list here, you probably know better than I do. You kind of know what the sort of benchmark program is right now. So when you go out, you've got a survey method like method 21 or an OGI, And that does two things, right? You've detected an emission and you've also located it. And then you have a repair package that comes after it. When we look at the next generation methods, and if you think about what we're trying to do with feast here, we're really trying to compare multiple methods together. That's the equivalence part of the pathway to equivalence. And so what you heard about from Chandler and Ellen so far is this more complicated process where you have multiple tiers of programs kind of fitting together in a tight way to potentially do more detection in a shorter period of time or more effectively than you would with that original program that was on the previous slide. Okay, and that involves some partial detection that has some uncertainty to it, followed by a dispatch of another type of detection method, which also has uncertainty, but potentially much less uncertainty. And then finally, this dispatch of this repair team afterward that's going to come there and fix the leak. And as one of the questions that was in the question box a few minutes ago is, what does a repair even look like? We're debating that right now. It's kind of like, is it just tightening something that's going to get loose again, or resetting something that's going to start leaking again? Or is it kind of repairing it in such a permanent way so it doesn't happen again? So what we want to do is capture in the simulation of the emissions, all of that complexity. So if you back up a bit, that comparison that you saw with feast right now, the key thing that we want you to walk away with is that feast model is comparing one program to another program. It's not comparing a method to a method. It's comparing a program to a program. And so that means that there's several methods potentially involved. Okay, those are packaged into a program which involves dispatching the methods, behavior of those methods, and then some type of work practice that follows that, where we know when we're going to dispatch, what kind of time it's going to take us to correct a leak, and that type of thing. Okay, so we're simulating this big yellow box in feast. And as a reference part, feast also has its own way of simulating emissions. That way, feast can stand by itself, okay, or feast can be coupled with meat, as you just saw in the previous slide. Okay, so in order for this whole package to work, we need something that's going to model emissions in a really effective way. So we know the size, the frequency, how often it occurs, where it occurs, what type of site, how it's impacted by weather, all that type of stuff. We have to get the expected emissions right. Then we have to get the program simulated the way you just saw, quote, right. And then we can get out of that a statistical result that's how much emissions we've mitigated. Okay, and then we can compare one program to another program to another program, and we can tell if they're equivalent or not. So to make this happen, we need a couple of components to come together at once. And one of those is that we need test results. So we need to be able to characterize each of the methods, and they need to be characterized for kind of the site type, for the weather conditions, et cetera, in which they're deployed. Okay, and it turns out testing is expensive, as you all know, and it's also seldom possible to get all the bits and pieces that we need to get a perfect result from the testing. So we're always in a compromise situation of, do we have enough data, or if we had another dollar to spend, what kind of data would we go get to improve it in the maximum amount? And then we're going to simulate this whole program, and that's what you saw with Feast right now. And one of the big changes we're making to Feast, or I should say our partners at Harrisburg are making right now to Feast, is this idea of being able to simulate the whole program, and in very complex programs with sort of multiple dispatches. Okay, so in order to put this whole thing together, the CSU team and our partners at UT Austin, UT Arlington, and Harrisburg, with the help of a lot of investment by industry and the Department of Energy and others, are putting together this sort of suite of programs that together can implement that entire box you saw on the previous chart, right? So UT Austin, ourselves, SLR, are working on the MEAT model, which will characterize emissions. And while it says methane emissions estimation, it also does non-methane bits. Okay, we've got a program that Clay's going to talk about in a few minutes that is related to how we're testing and how we get repeatable testing. done for methods. And then what you're seeing right now is the simulation of performance using the feast model and the extensions of that feast model. So hopefully that kind of gives you this bigger picture context of how we're trying to bring all of these pieces together. I'd like to take a moment right now to also thank all of our project sponsors. So BP, Chevron, and Environmental Defense Fund are the current sponsors of the PTE project, and they're ongoing sponsors today of the work that you see here. Also, I'm very excited and impressed by the number of people online. I think when we started setting up this webinar, we were kind of shooting for 20 or 30 people, and we had over 100 a moment ago. That really, I think, illustrates sort of the enthusiasm behind this type of an approach. So I'll handle the slides for Clay, and I'll pass it over to you to talk a little bit about the next steps.
Great. What I'm basically going to present a couple slides on is the added program. So the motivation behind added, sort of as it's proposed, is to take solutions from the controlled testing through controlled testing, field testing, and the simulation tool with Meet and Feast, and reconcile differences and try to demonstrate that with this approach, if you have an accurate representation of the performance metrics of your methods, and you put that into Feast, and you have an accurate representation of the emissions profiles for your field sites, and you put that into Meet, and you run those two models together, then you can predict what the method deployed at the field site would potentially see. And the idea is to develop protocols for testing, evaluate run some methods through those protocols, deploy those same methods in the field trial, and then reconcile the differences of what we observe in that field trial and what the Meet and Feast and the pathway to equivalency package would predict we would observe at that field trial. Dan, so next slide, please. So as the first part of added, we've developed some controlled testing protocols, and the real focus and driver behind those protocols is to evaluate these key parameters that are used by Feast. These are the meta parameters that Chandler discussed that represent how well does a particular method work on a particular class of emission and meteorological conditions, right? So we've developed these methods with the protocol development committee. We have over 75 members in that, from oil and gas operators, solution developers and service providers, and regulatory agencies, as well as some academic groups, to really drive how we would go about testing methods at a controlled site like METEC and produce these metrics to feed into the model. So we're going to be running through the protocol testing at METEC. So if you have a method that you're interested in running in Meet or in Feast, there's an opportunity to test both continuous monitoring solutions as well as survey solutions this spring and summer using these protocols. And again, they're really focused on evaluating the metrics that you would need to represent that solution inside of the Feast model or the Meet and Feast combination. So if you're interested in added protocols, if you have questions about what the test protocols look like or would like to have a copy of them, if you're interested in what the metrics are, there's additional metrics besides the probability of detection curves. So we also are able to look at quantification accuracy or localization accuracy and precision in those test protocols. We're also, if you'd like to discuss the test schedule or the participation in a testing window, or if you're interested in using that protocol in a different time frame, please go ahead and reach out to myself or Dan, and we'll send the info your way and get you updated.
Great, thanks, Clay. So this is the advertising segment of the broadcast, right? So we're looking for your engagement, and we have some examples here. I'm not going to drive through every one of them, but we're really looking for sort of three things. The first one is we need people to go through testing that's controlled enough that the resulting data can be used in these simulations. And to the extent that you're an operator or encouraging a solution developer, we would really appreciate that. The second thing that we need is we're looking for data that will give us an accurate representation of emissions. And so to do that, we really need your data about, your frequency of the frequency at which you went and looked for leaks and how many you found, et cetera. And then I think the third thing is that we are searching for test cases where we can do equivalence comparisons on a realistic scenario. So by region or by company or that type of thing. And so in fact, our objectives as part of the PTE program in 2021 is actually to identify a couple of these and make them happen. And so we're interested in your input on that as well. Okay. And I think with that, we can switch over to Q&A. And if we can get all the speakers to turn their cameras back on, we can field questions through the Q&A box. And we can also highlight or elaborate on some of the answers we already gave. I think, Arvind, you had one that you were reserving for verbal. So we might want to just start there.
Sure. So this question, I think this is applicable to a lot of different technologies. It's about whether there have been conversations to agree on a median detection threshold for different technologies. I think this is a great question. Most of the technologies that are being modeled in Feast right now, the data are based on data we have collected through field studies at METEC and at other test locations. But if there's a scenario where for regulatory purposes or other reasons, we need to specify a median detection threshold that's already approved, we could use that number in this model to compare other programs with.
Great. We have another question. We could probably just answer live from Philippe. Felipe, it's would be nice to add VOC emissions even if the technology detects only methane and track the VOC reductions based upon emission ratios of VOC to methane and where the emissions are originating.
And this question was already answered, but I want to highlight it because it really tells speaks to the use for meat feed score simulation. As Dan highlighted, we model LDAR programs, not specific technologies. And too often we see just comparisons of detection thresholds to suggest whether a technology would be good or bad in a given scenario. I think what this model helps us do is understand the context of technologies within leak detection and repair programs. We have several variables such as survey frequency, such as dispatch rules and repair procedures that end up affecting the mitigation outcomes. And using a model like this would really help us understand the trade-offs and synergies between different programs and approaches.
And let me also add that we're going to do an experiment in the DJ Basin starting this spring, and probably the big field campaign will be in the fall. And part of that will have a chance to test, at least more from meat than feast side, but testing the modeling of speciated emissions and comparisons to field data for that. We had a question from Matt Harrison. You mentioned handling quantifications in the next version of Feast. Can you comment on the time frame for that?
I can start. So I think we've been working, actually Alan has been working on integrating that into the Feast model. And it's kind of at a beta stage inside here. So I think that'll definitely be included in the next revision that's released. And I'm not sure what the time frame on that would be. So
And the way these releases typically occur when we have additional features added to the model is it won't be a public webinar every single time. We'll send email updates showing, hey, we added this new module to the Feast platform. The updated code base is now available online.
So there's a question from Alex. Have you engaged directly with the EPA on the use of the Feast model? Which other regulators have you directly engaged with? So I can say we've had some conversations with EPA, but I would stop short of it saying it was a heavy engagement at this point. They're quite aware of what we're doing, let's put it that way. And there are representatives from EPA on the protocol development committee, for example.
Yep. And we, of course, work with state regulatory agencies in Colorado and California, given that many of the field work studies are actually happening in those states as well.
I would add that EPA had a public comment last year that said, they're aware of the kind of controlled testing results and field sites, and they're aware of modeling approaches, and the statement said they're willing to consider those in addition to, but not in lieu of, field data for, say, alternative work practice.
Great. So I'd like to comment also on a question Stefan asked in the Q&A a bit ago, which was, does the model distinguish between the types of repair that are being done? And so that, and I answered it in the text box, but I just wanted to bring out a little bit more detail on that. So this is an area that we're actually debating right now, right? Because you can think about a number of different behaviors for an operator, like a pumper on a site, where some repairs may be temporary or maybe just like resetting something. Others may be complete replacement of equipment to mitigate emissions. Those have been very hard to find data on that. Okay, so right now our repair process is quite simple, and Chandler could probably wax philosophical on the details behind that, but right now it's sort of like a binary thing. If something's detected, it's repaired, it disappears, and we have some ways in meat of making things reoccur if necessary. So that's a fluid area is the bottom line. And I think Stefan knew when he poked that question out that he was stirring up an area of great interest. So, okay, we've got a couple more questions in the Q&A, and then I think we should probably switch over to the tutorial. So you all can read the Q&A, right? So.
Yep.
Okay. Arvind, you want to take Matt's question?
Sure. So the question is, just for the sake of others, what is the feasibility of controlling responses to vented sources? That is not just ignore them, but fix according to some rule. And the second part of the question is feasibility of changing the response to a vent depending on what the underlying source is. So this is something we've been discussing, and it varies a lot by jurisdiction on how vent-related emissions are. Right now, the way we are modeling in Feast is basically limited by what the technology can do. For example, a continuous monitoring system on the site will throw up a flag when it detects a large emission from a vent. There's no learning involved, so it doesn't get fixed immediately. But this is things like this, adding dispatch rules and repair rules for vent-related emissions can be added into the model if we have enough data.
So I see a question here from Robin. The question is, does the model help evaluate the timing of repair? And that is supported at this point. So when we define a repair method in the model, you can specify some delay between the detection and when the repair actually occurs. And so you could run multiple simulations with that value set to different time delays and see what the effect is. The question goes on to ask, can you differentiate even further by timing of repair depending on the type of component detected leaking? And that's not supported at this point. So a repair method is not sensitive to the type of component that's leaking. in this release.
It was Anna's question. Yes, we will also record the tutorial, and that will be available on YouTube. And Lindsay's question regarding the use of the model. There are no restrictions on the use of the model. Everything is publicly available. As soon as we have updates on new features, we'll push that onto GitHub. So yeah, feel free to use the model, give us feedback, or if you want to collaborate with us on using the model and developing jurisdiction-specific inputs, we can help with that as well.
And the coupled version of Meet and Feast will be out later this spring. I would say late spring, based upon where we are right now.